There's a great deal of information in the slides, and that's why I always do a handout, because it enables you to flash back or take it away after the talk. Go ahead.
Well, I just wanted to say a word. I mean, a man who perhaps needs no introduction, but I just wanted to say a word or two because in many respects, this conference is only happening because of George, because well, I want to say many years ago, who knows exactly how many years ago. George is certainly known for teaching a famous course on Newton at Tufts, and he came over to Stanford, and he gave the Newton lectures that have now become the paper Closing the Loop. He also taught an abbreviated version of that course, and it's only because of things that happened in that course and a certain way of thinking that George influenced both me and then also Teru, who we'll hear from this afternoon, that I got started thinking about measurement in the way I have been, that led me to this topic of the fundamental constants that led to this conference. So in many respects, none of this would be happening without George, and so forth. We're very excited to hear his particular take on constants, which is kind of closely guiding the work that Teru and I are doing in conversation and collaboration with him. Thank you, George, for coming all this way. We really appreciate it.
Two preliminary remarks. First, it's humbling to be talking here with 4 people in the room who were in that 2009 Stanford course, as a matter of fact, a substantial fraction of the room. I'm not going to be giving you a take on, or maybe you will consider it a take, but I do not have answers about fundamental constants. I've been thinking about them for almost 35 years, and for 15 years spending a great deal of time with the physicist Ken Wilson talking about them. I do have a book coming out, originally an undergraduate paper. It's now co-authored with Raghav Seth, but a 400-page book on the measurement of fundamental constants between 1905 and 1913. And some of this will reflect that for what it's worth. Anyway, the theory-mediated measurement goes back to Ptolemy. So that's not the key term in the title. The key term is interlinked. And so what I'm going to do is give a history of the logic of measurement of interlinked constants, starting with Planck's famous 1900 paper, indicate ways that's giving us evidence, and then turning to questions about exactly what it's evidence for. Let's see if I can. So I have to say a few words at the beginning about how I talk on theory-mediated measurement. Between 1659 and the mid-1660s, Christian Huygens developed 4 different ways of measuring what we now call small g, the acceleration of gravity. He was measuring the distance of fall in the first second without air resistance, something that nobody had successfully measured. I'm showing 2 of those ways. One of them is a small arc circular pendulum on the left, and the one on the right is a conical pendulum in which the bob is confined to a paraboloid surface. The key word here, well, the most important thing to introduce is a jargon term of mine. The 2 equations at the top I call measures. A measure is an equation that allows one to infer values from less accessible quantities from more accessible quantities. And I'll be talking the whole time about measures. For a measure to be stable, as I use the term, I've now just recently discovered others have been using the term somewhat the same way, is as you change all the manipulable parameters in your setup, you should continue to get exactly the same constant. So Huygens changed the lengths, he changed the bobs, changed the material, etc. And both of these measures proved to be stable. My comment is if a measure doesn't prove to be stable, you're not actually measuring a constant, period. But it's equally true for stability when you're doing a functional relation. Just a little bit about the logic here, it doesn't matter much. The stuff in blue were principles that had been independently verified independently of Huygens' work. What had not been verified is the constancy of gravity vertically. And the fact that his results came out stable convinced him that gravity was uniform near the surface of the Earth even after the Principia appeared. The other key thing, terminology here, is convergent measures. The striking thing here is these are two complementary measures. If you look at the stuff in blue, they have the assumptions, background assumptions have no relation to one another. One's a forerunner of Newton's first two laws, the other is purely Galilean kinematics. And they yielded the same value, 15 Paris feet, 1 inch for the distance of fall in 1 second. It's actually a little better than that. When you look at Huygens' notebooks, it's into the fourth significant figure, very near our present measures for the locations in question. And the point that is somewhat controversial, but I've been insisting on it for years, well-behaved results from a measurement are evidence in themselves. When it's stable, it's evidence that the presumed constant is actually a constant and that the measure itself at least holds empirically. It doesn't tell you that what you're measuring is what you think you're measuring, but you do get that when you get convergent measures from complementary measures. If you have totally different background assumptions coming to the same quantity from different views, the two agree. That's grounds for saying that the theory is telling you what you're measuring. So we've got the physical validity of the measures, the physical interpretation of the constant, and you get derivatively some evidence for the background assumptions. There's a third category that I lean very heavily on. I call it amenability to increasing precision. First, let me describe it with Huygens' case. Huygens was quite preoccupied with precision on this measurement. So one of the things he did famously was solve a problem, namely it's called the center of oscillation problem. But what he allowed him to do was to measure the length of the pendulum not to the center of gravity of a bob, but to its center of oscillation. And it turns out of his 4 measures, only one has the center of oscillation well defined because the other 3 have varying lengths. So from his point of view, only his small arc circular pendulum measurement admitted of increasing precision, and he stresses that. For what it is worth, how good is it? We were still using his measure in the 1950s, now to 7 significant figures for measuring surface gravity. So it took a long while to replace that measure. It got much more elaborate with more corrections. Now, all of this, I say, is to a certain level of precision over a certain envelope of applicability, using Glashow's term, stated in terms that are at least proxies for yet to be discovered terms having greater theoretical significance. I take this to be true of everything in physics all the time, the statement. Let me illustrate it here. Is of course the level of precision. It is not exact because it's assuming constant gravity acting along vertical lines. Newton took the trouble to derive the Huygens measure in the asymptotic limit from his universal gravity, confirming it's at least good to 7 significant figures in the asymptotic limit. In terms of yet to be discovered terms, we of course replace this with the acceleration of gravity, which is a far preferable term to the parochial distance of fall in 1 second. The most interesting one, though, is over a certain envelope of applicability. It does not hold as you go up vertically, but more significant, Huygens' dream was that it would hold everywhere around the surface of the Earth, and he could then use the length of a 1 second pendulum to give a universal standard of length around the Earth. To his disappointment, it did not. Okay? So all of these count, and they're all significant. There are a lot of examples. I just chose 5 of the more famous ones where theory-mediated measurements led to truly important historical discoveries. Newton's so-called moon test used Huygens' measurement of surface gravity and the inverse square relation to confirm that terrestrial gravity extends into the celestial realm, quite famously. Maxwell's grounds for saying that light is electromagnetic waves, as he could calculate the velocity of electromagnetic waves. He could compare it to the speed of light. They were close enough that he then concluded light is electromagnetic waves. A more striking case is the gas constant R. It was originally developed in terms of density, but then various materials, my favorite example is nitrogen dioxide, which at our present room temperature is pure nitrogen dioxide. You drop it down near zero, and a large fraction of it becomes nitrogen peroxide into O4, and of course, therefore, the density stays the same, but the gas constant is totally different. That's how we got the mole, was the variation with temperature of the gas law, and got replaced with mole density. Isabel has just talked about the measurement of the gravitation constant. The one thing I'm adding is Zenneck in 1901 in a review article in the German Encyclopedia on gravitation pointed out that if it weren't for the experiments that Isabel described, the collection of them, we would have no grounds for saying that gravity varies with the mass of the attracting body, other than by assuming the third law of motion applies. So those actually constituted the first evidence that capital M belongs in the numerator. Okay? It had been just assumed for 150 years before that. And Zenneck makes a nice big deal of it. Then there's a case that both Isabel and I have written independently about of Thomson's converging, and I emphasize, order of magnitude measures for the mass to charge ratio of three different phenomena, yielded in 1899. The negative ion is the fundamental quantity in terms of which all electrical properties can be expressed. And following that, the total asymmetry between positive charge carriers and negative charge carriers. Okay? All of those come out of theory-mediated measurements. None of them involve interlinking. So let me turn to interlinking. Planck developed his famous law of black body radiation after earlier committing himself to a prior law and then discovering it didn't work with across the board on temperature. His first approach to it at the top, E is energy, and he has two constants, capital C and small c. It's a pure curve fit. There's no physical account of what the two C's are. He then went back and did a very novel interpretation of Boltzmann's theory of entropy, which was extremely controversial at the time. Did a very novel interpretation of it to derive the famous law, which is stated in terms of energy density, and took the data to get his two constants, H, which we still retain, and K, which we still retain. He named K Boltzmann's radiation constant. Boltzmann never called it anything like that. Boltzmann never thought it could be measured. And then proceeds to derive, it's more than I'm just listing here, but he derives from K three further values. Avogadro's number, the charge, e to the 4.469, and the mean translational energy of molecules, which is 3/2 K. And then he adds, this is the final paragraph of that very famous paper, if the theory is at all correct, all these relations should not be approximately but absolutely valid. The accuracy of the calculated numbers is thus essentially the same as that of the relatively worst known, the radiation constant K, and is thus much better than all determinations up to now. To test it by more direct methods should be both an important and a necessary task for further research. In effect, he's saying he's got this crazy derivation. What's the evidence for it? Go out and measure these other things in independent ways and confirm that you get his values. So he's simply proposing a program. How did he get those values? Well, he was the first to say in print the full appreciation. He had two known 19th century values. I'm giving values stated in 1890 by Ostwald for the two constants. Faraday's constant is the amount of electricity needed to generate in electrolysis 1 mole of a univalent material, univalent substance. And of course, you know the gas constant. The point is, if you do accept some form of molecular theory, then the gas constant should be K times Avogadro's number, and Faraday's constant should be a basic charge times Avogadro's number. What that means is if you have one of these three microphysical numbers, you have all of them, okay? They are interlinked by the Faraday constant and the gas constant. And that's exactly what Planck was trading on, okay? They actually give you a lot more. If you've got Avogadro's number, you've got the mass of a hydrogen molecule, which means you've got the mass of a hydrogen atom, which means you have the mass of every atom, which means you have the mass of every molecule for which there's a chemical formula. All of that pops out from any one of these values. And that was recognized. I don't know how many recognized it before Planck, but after Planck, it was very widely recognized. And I raised the question, is this a way of gaining experimental access to the microphysical realm? Just for your background, Planck was very anti-atom until the mid-1890s, very slow to accept atoms. So Planck created a program. The program didn't come to fruition very fast. Harold Wilson and J.J. Thomson published a new value for E that was totally discrepant with Planck's value. Einstein, in his dissertation of 1905, made the proposal that the mean kinetic energy in Brownian motion is the same as the mean molecular translational energy. And he threw out some numbers, but the numbers were purely conjectural. So the first actual success in print at fulfilling Planck's program was an extraordinary pair of papers in August 1908 by Rutherford and Geiger. What they did was to take a very small, I can't do it with my fingers, tube against the surface of radium so that they could count alpha particles coming through the tube and then extrapolate from that of the total rate of production of alpha particles of a mass of radium. And the tube was fine enough, of course, this is the forerunner of the Geiger counter, I trust everybody realizes. The tube was fine enough that they were getting an alpha particle roughly 1 every 2 to 5 seconds. They could literally count them one by one. They could accumulate them at the electrometer. They knew the number, they divided, and they concluded 2E. And they say here, considering the data, well, the number they get is 9.3 times 10 to the minus 10th ESU. And now the quote, considering the data as a whole, we may conclude with some certainty that the alpha particle carries a charge of 2E and that the value of E is not very different from 4.65 times 10 to the minus 10th electrostatics unit. Elsewhere, they do make the claim, and they do cite Planck's value, and they make the claim that these are the first 2 reliable values ever attained for E, which they were right about. And the end of the paper, they give their own value of Avogadro's number and their own value for the hydrogen atom mass. These are spectacular experiments that somehow have gotten lost and need to get a lot more attention. Probably in response to the Rutherford paper, Paren had been working for 3 years on Brownian motion experiments, at the time unaware of Einstein's dissertation. Langevin finally called his attention to it. But this is a paper, the third page of it runs only about 10 lines, so you're seeing the whole paper here. I only did this right-hand page in the handout, so you could at least read it if I put the whole page up. And he says various things. He refers to different people's measurements, including the Planck measurement at the top. He mentions the Rutherford and his beautiful memoir. Geiger didn't get included, but it is jointly published. And says then that he has a way of doing it. His way is to indirectly, theory-mediated measurement of the mean kinetic energy of granules in Brownian motion from their vertical distribution at equilibrium from the effect of gravity. And he announces that he has obtained from this, his way of doing it is direct and susceptible to in unlimited precision. And he gives three values: 71 times 10 to the 22nd for Avogadro's number, 4.1 for the charge, and for the mean translational kinetic energy of molecules, 1.7. You should notice these numbers are a good 10% off. In fact, these numbers are 15% off the Planck and Rutherford values, okay, for what it is worth. Paren's going to do more, and I'll come to that in a moment. There's one experiment that's sort of gotten lost historically. It's very hard to find literature on it unless you go back to the time. It's one of the most beautiful experiments I've ever seen. Boltwood was an American. He had gotten to know Rutherford at McGill when the two were there, and he spent 2 years, year and a half at Manchester, and he did an experiment taking off from the Rutherford Geiger. His idea was to collect individual alpha particles. It takes a few months, a few weeks anyway, to collect enough to form a gas, but he systematically did so after verifying their count, so he actually knew the number of alpha particles forming the gas. Spectra showed the gas was helium, okay? So he had a gas where he knew, under the assumption that alpha particles retain their individual integrity when they lose their charge and become helium, under that assumption, he knew the number of molecules in his gas. And that enabled him to measure Avogadro's number from the measure that I'm showing up there, and got a number, by the way, along with one other, was the best number anybody got before the 1930s. Nobody realized it was the best number, but it's extraordinary. And then he ends the paper with the remark, there can be no doubt that the alpha particle during its flight consists of a helium atom carrying 2 unit positive charges, and that helium is monatomic. The agreement between calculation and observation verifies in a remarkable way the essential correctness of the atomic theory of matter. From these 2 experimental observations, it is possible to deduce with a minimum assumption the number of atoms of helium in 1 cubic centimeter, 2.69 times 10 to the 19th. My 60.3 is obtained from his number by multiplying by the magic number, 22,400 and a little change. What I'm going to turn to now is the Solvay conference. Rutherford, Planck, Rutherford, Paren sitting to the left of Madame Curie, etc., held in 1911, as I trust most of you know. The subject was how to reconcile the quanta of Planck and the quanta Einstein had proposed for specific heats with classical physics. It's the first Solvay conference. Solvay, who a wealthy industrialist, not a physicist, who paid for all of this. The numbers shown on this slide were all the ones not in brackets were discussed at the Solvay conference, openly discussed. The ones in red are the correct, giving the correct item that was most directly measured. Paren always insisted on giving as his measurement results Avogadro's number, but he was doing it through measuring energies. A couple of remarks. You've already seen the Rutherford Geiger. Regner, independently of Rutherford and Geiger on the continent, verified their experiment and in fact did it somewhat better. His numbers turn out, along with Boltwood and Rutherford, to bracket our present value. Warburg was confirming Planck in his lecture at the Solvay conference. Milliken had just announced his first oil drop experiments. He was not at the conference. No American was at the conference, invited. Within 18 months, Milliken had revised his number. The new number for charge was 4.774, and the new number for Avogadro's number was 60.62. The interesting thing are the Paren experiments. Paren was the one, Warburg and Paren were the two people to discuss these numbers at length. Paren talked, it's the longest paper in the proceedings, substantially the longest paper in the proceedings. It was entitled The Proofs of Molecular Reality. And he was charged with going through all the arguments that molecules are real. And in part of that, he presented his more recent work from Brownian motion. By then, he had 4 different ways, 4 different measures in my terminology, for obtaining molecular constants. 2 of them were done with single experiments, the diffusion experiment and the rotation experiment. The other 2, the vertical gradient and the displacements, which is the Einstein method, those are remarkably beautiful exercises in theory-mediated measurement. He varied in several different steps the sizes of the granules. He varied the liquid. He varied the temperature in both and got very much well-defined numbers, the 3 significant figures shown for Avogadro's number, or the numbers that he actually got. Now, his problem was he was measuring the mean translational kinetic energy of granules, which are a couple of orders of magnitude larger. His smallest are a couple of order of magnitudes larger than the largest molecule in his fluid. And he was simply assuming, stipulating, that the energies are the same. If you notice, his numbers for the energies are more than 10% below everybody else's. His numbers for Avogadro's number are more than 10% above. This did not go unnoticed. The German edition of the Transactions, edited by Nernst's assistant, Eucken, calls attention to this discrepancy. Okay? But this is where things stood in 1911. Planck published the 2nd edition of his theory of radiation 18 months or so later, and expressed with some pride that all these numbers had now shown he was right. Okay? And Poincaré said at the time, we now have Avogadro's number to 1 significant figure. We thought we would never do that. But that's about all that can really be claimed here. 1913, 1914 saw, of course, the major breakthrough of the Bohr model. There's only one piece of empirical evidence in the first paper, the paper on hydrogen. Namely, from his model, Bohr can calculate from first principles what the value of the Rydberg constant ought to be. And of course, it's a known value. So he does so using the 3 values I'm showing and obtains what he claimed. The agreement between the theoretical and observed values is inside the uncertainty, et cetera, which, depending on what you think, might be true. I'll come back to that in a moment. Bohr's model was not immediately accepted. One of the problems was it didn't work for helium at all. But there was a element in the spectrum of the sun that the origin of which was unknown. And Bohr looked at it and made a 2-fold proposal. The first proposal, the proposal was it's the helium ion, 1 electron, so his theory applies. But in the process, he decided that his original calculation of the Rydberg constant needed to be corrected for a Newtonian 2-body effect. The electron is going around the nucleus, but the nucleus is in an orbit of its own. So the correction that is put in here is the one that Newton devised in 1687 for the variation from planet to planet. And this was a very important piece of evidence for the Bohr model that he could explain this yet unaccounted for. Now, the 3 things to notice about the formula at the top. First, every quantity in it could be measured independently of all the others. Okay? So the fact that you get any agreement there at all is quite independent of the theory, whether they agree or not. Had Bohr chosen the value Milliken had made available at the time, 4.774, the agreement would have been within 1%. Okay. Finally, if Bohr had chosen Paren's value, which is 4.1 or 4.2, depending on which one you want to do, it would have been off by more than 50% because of the fifth power of E. After 1914, the only person Rutherford and I have been able to find who still applauded Paren's numbers was Paren himself through 11 editions of his Les Atoms all the way to 1922. The philosophic literature has built off of Paren without realizing that his numbers were totally discredited very early on. It's just an interesting point. Okay, 1916, we have another two important developments. One is Milliken taking a proposed relationship that Einstein had derived in his photoelectric effect paper and actually verified it, getting a value of h over E, and from his value of charge, then giving a value for h. And the paper is actually entitled A New, More Accurate Value for Planck's Constant, or for h. A striking thing to notice about that is that as Milliken goes on, he makes the following point about Einstein's quanta of light theory. I'm almost quoting. This untenable theory, it would appear Einstein himself is finally recognized as untenable. That's in 1916. Einstein had not. Milliken was quite mistaken about that. But nobody was accepting quanta of energy at the time, but Einstein. Okay, he was alone. Then the other significant thing that's been discussed by others here, to account for the splitting of lines in the hydrogen spectrum, Sommerfeld proposed that, again coming off of Newtonian theory, at the same energy you can have elliptical versus circular orbits. In an elliptical orbit, when the electron is nearest the nucleus, its velocity can be much higher, high enough that relativistic effects take over, and from that he derived an expression for what the splitting of the lines should be, and from that gets the formula for the fine structure constant. That's from his 1916 paper. I'm going to continue to do what happened afterwards. We almost always present the number for the fine structure constant in terms of its inverse, partly for the odd reason that 137 is a prime number, and there was a period of time where people worried about that. I learned physics initially from Boris Podolsky, and he made wonderful jokes about God doing us a disservice by giving us a fundamental constant as a prime number. So I'll be continuing with that. Fair enough? So now we've got the Rydberg constant and the fine structure constant, the Faraday constant, and the gas constant, 4 ways of interlinking the microphysical constants to one another, and they're still independently measurable from one another. This is from the English translation of the 1921 edition of Atomic Spectra and Atomic Structure, the Bible of the old quantum theory by Sommerfeld. What's interesting about it here is his proposal. He wants to take the Rydberg constant for hydrogen, the Rydberg constant for helium, both of which are known to reasonably high accuracy, and the value of his fine structure constant, and use those to create new units. And so he goes through the exercise inferring values of E and H and M from these macrophysically accessible quantities. He looks at the error bars on them, is disappointed that they're not precise enough, and then at the bottom of this page, he proposes, let's bring in Milliken's 4.774 value and get what he calls, I'm not sure it's in this slide, semi-spectroscopic fundamental units. I'm going to come back to fundamental units later, as you would anticipate. So that's 1921. By 1921, then, we have the following values of the 4 microphysical constants and 4 macrophysically accessible constants, and the formulas. I use squiggly equal sign in there because not everybody was using the same number. The one exception are the top 2. Everybody by 1921 was taking the Milliken value as as correct. And that also meant the Milliken-Avogadro's number. Planck got the Nobel Prize in 1921. In his Nobel Prize speech, he called attention to these numbers with great pride. His program had been fulfilled. Okay? The other thing to notice, though, is every one of these is independently measurable, except for A and K. They're just 3/2 power, factor of 3/2 with respect to one another. So whether these formulas hold here is simply it's a simple number question. Plug the numbers in and see how well they hold. The answer is they all hold within roughly 1 to 2% as of 1921. So all of these are taken to be relatively confirmed numbers to at least 3 significant figures, if not 4. I make the remark now in the text I prepared with this. This is the first time in the history of physics where there have been a series of quantities interlinked to one another measured to this level of precision. Okay? This is a unique event in the history of physics. It's not from lack of trying by others. Maxwell defined a program, phrase gaining experimental access to the microphysical realm is a phrase of mine describing his program, from the following. Take his theory of statistical mechanics, take his equation for the viscosities of different gases from the diffusion coefficients of different gases, from the Clausius virial expansion for the deviations from the ideal gas law. Later, others added the dielectric constants. But we have 4 macroscopically measurable quantities that vary from one gas to another. That's the important thing. And what he wanted to achieve was to infer from them the sizes of the molecules, the mean free paths they had with respect to one another, and the forces between them. That was a program that was pursued aggressively from 1870 till 1899. It's beautifully described in the second edition of O.E. Meyer's book. That book is totally devoted to all the experimental results from this program, from top to bottom. And it's a magnificent book. It's unique. Nobody else wrote a book like this. What happened is they did not get stable values. Their values for Avogadro's number, which is supposed to be a constant from one gas to another, wander all over the place. Okay, why? Well, I'm quoting Jeans in 1921. I could have quoted an earlier edition. The trouble arises primarily from our ignorance of the shape and other properties of the molecule. If the molecules were known to be elastic spheres, the question would be simple enough, and the size of the molecule would be measured by the diameter of the sphere. If, however, the molecules are assumed, his italics, as a first approximation to be elastic spheres, experiment leads to discordant results for the diameters of these spheres, and now I've added in for Avogadro's number, showing that the original assumption is unjustifiable. So Maxwell had a beautiful program. It failed. Okay? And it failed because of the need to assume spherical molecules. They are not a decent first approximation at all. And that's my comment. Maxwell was trying to do the same thing, interlinked constants, but he's simply having to assume a shape doomed his effort. All right, what I'm going to do now is start jumping. I'm going to go through 100 years listing milestones in measurement only. This is not the way to present history, but I've given you the background now. The 1920s, the most important single event from a measurement standpoint was the Compton effect in 1923. Let me explain that. If you take monochromatic or nearly monochromatic X-rays, hit metal, you get scattered X-rays off. Compton had been working for several years at identifying all the wavelengths of the scattered X-rays. One of them was invariably the monochromatic incident. All the others but one were the spectra of the material that you were hitting in the X-ray. One was open. He called it originally a fluorescent wave. And he finally characterized it enough to try the following. Let's assume the most elementary mechanical principle of two perfectly elastic spheres colliding and going off at different angles. Oh, by the way, the important thing, the wavelength he could not attribute to anything varies with scattering angle, but differs from the incident wavelength only slightly. So he simply said, take the equations for elastic spheres, let h nu be the energy of the light, let h nu divided by c be its momentum. Let's see what we get. What we get is that formula. What's in red is called the Compton wavelength. It's one of the fundamental constants, giving a new way of doing it. This is from his original paper showing the degree of agreement. In his dissertation, Roger Stoyer called this a turning point in the history of physics. This one experiment ended all resistance to, well, ended up ending all resistance to wave particles. The sequence is striking. It's 5 papers coming out of Copenhagen, starting with Bohr, Kramers, and Slater proposing to abandon conservation of energy and conservation of momentum as absolute principles, treat them only as statistical approximations. Geiger quickly showed that doesn't work. Then you had 2 scattering papers by Kramers, a 3rd paper by Kramers and Heisenberg, and then Heisenberg, on his way back from Copenhagen to Germany, starts drafting the famous paper of 1925, in which he abandons all talk of electrons being in definite orbits. Okay? With that, we get the new quantum mechanics, which forces the Dirac to do a new relativistic quantum mechanics to replace the Sommerfeld relativistic. And interestingly enough, though he doesn't do this, Darwin, in a subsequent paper, showed that Dirac's paper actually does work for the hydrogen spectrum. The fine structure constant and its equation pop right out. What does that tell you? That equation is far more robust than the theory it's derived from. The Sommerfeld theory and the Dirac theory, the only thing they have in common is special relativity. Okay? So that's become a fixture. The other thing that's striking in the 1920s is Raymond Burge, a spectroscopist at the University of California, Berkeley, decides that there's too many apparent discrepancies in the literature between different authors because they're simply using different values of constants. Why not put out a paper with preferred, his word was probable, values of the constants? And that starts the sequence that goes to your situation right now. This he did entirely on his own. 1930s, there's one really important event. It has not received the attention in the literature that I think it should. By the 1930s, X-ray crystallography had reached the point that you could actually measure grading constants relatively precisely enough that you could do it for a constant. His case was calcite crystals, Bearden's case. And you had this formula sitting around for a long while for Avogadro's number, if you could get grading constants to a high enough precision, and you could assume the crystal is perfect. That's a key assumption here. So Bearden does this, reaches a value of 60.19 for Avogadro's number with very tight error bounds, and from that you get a value of 4.806 for the charge, and of course it stands in sharp contrast to Milliken, so he concludes there must be something wrong with the X-ray crystallographic work. He continues to work on it. By 1935, as you can see, he's got another significant figure. The error bands are really tight at this juncture, and all he can say, while the above methods of determining E and H are apparently correct, the results obtained are difficult to reconcile with existing data obtained by other methods. At the present time, there seems to be no satisfactory explanation of this dilemma. What happened then is that in at least 3 different laboratories, people decided to repeat the Milliken experiment. And what they discovered is Milliken used the wrong value for viscosity of oil drops in air. creating a systematic error that pervaded almost all the measurement of the fundamental constants up to 1940. Once you get the correct viscosity in, you replace 4.774. This is Burge in 1945, where he reviews the story, 4.8071. As part of that, though, they concluded, and this is now I'm paraphrasing Burge, we will never be able to measure the viscosity of oil well enough that we will be able to go to higher precision. In my phrasing, oil drop experiments are not amenable to increasing precision. As of this juncture, they become just part of history. They ceased being of relevance to any of the measurement of the constants. Avogadro's number from then until today is primarily being measured through X-ray crystallography. Is that fair? Primarily.
And also maybe some gas telemetry.
Okay, fair enough, fair enough. 1940s. The most important event was the Shelter Island Conference in 1947, where for the first time the theoretical physicists held a conference and decided to invite a couple of experimentalists from Columbia University to come the length of Long Island. When they got there, well, back up first. During the war, there were really major advances in technology that could then be adapted by physicists into a laboratory. The most important is microwave technology. Microwave technology enabled Lamb to show something that many had suspected, namely the Dirac theory for line splitting is inadequate. The line splitting is much finer than had been realized before. And out of the same laboratory where Rabi is the key person, you get the same discovery about the anomalous magnetic moment of the electron. That too is a violation of Dirac's theory. Okay. Between 1947 and 1950, you have the Beta, Schwinger, Tominaga, who was not at Shelter Island, Feynman, and Dreisen formulate QED. And of course, once again, the fine structure constant pops right out, but this time it was a constraint. QED had to supply that, okay? It being so robust. With it, you get two new ways of measuring the fine structure constant, one from the hyperfine structure of hydrogen or deuterium, the other is by the anomalous magnetic moment of the electron. Between 1950 and 1970, there is a radical transformation in the field of metrology. It starts with two of the protégés of Burge taking over the responsibility of providing preferred values for the constants. But they get serious about something that Burge had only toyed with, namely using least squares method. The idea is very easy to explain. It was used in orbital astronomy from the 1860s forward. Take your best values of constants, plug them into what I'm calling measures, where many of them occur in pairs or in triplet, compare them to the macrophysically accessible ones. When you do that, you're going to get deviations. Fine, take those deviations, plug them into a weighted least squares, get corrections to all the microphysical constants to get the least square deviation of all of them. And that gets instituted by Cohen. Dumont and Cohen gets justified in a book of 1957. Cohen and Dumont come up with new values for the constants of physics and chemistry in 1965. As Nadine said yesterday, CoDada was created in 1966. In 1967, there's a paper, you can see the names. They had used the value of the 2E over H from the Josephson effect to conclude that this was a way of testing quantum electrodynamics, because the Josephson effect is at most weakly dependent on quantum electrodynamics. It gives you a value for the fine, you can infer a value for the fine structure constant, do it, and test quantum electrodynamics. That was followed by one of the most important papers in the history of metrology, 1969, Taylor, Parker, Langenberg, where they now give you whole new constants pointing out that the Josephson value of the fine structure constant is incompatible with the values coming out of QED. To tell you how important that was, it's a 140 or 150 page article in Reviews of Modern Physics. The Reviews of Modern Physics in the same year published it as a hardbound book under a different title, Fundamental Constants and Quantum Electrodynamics. With it, before these two, this paper and this paper, the point of getting values for the fundamental constants was to supply the community with a set of values. After these two papers, it was to test QED. Okay, so there's just a complete flip. The task force was formed in '69, and in 1970, there's this giant conference. I chose the photograph to drive home how many people were engaged in the fundamentals of metrology in 1970. This is not everybody. Some people were off at lunch. The volume from that is a volume that anybody who studies metrology ought to study. Okay, I mentioned it a couple times yesterday. I'd been mentioning the Josephson effect. There are two others that emerged after 1970. The quantized Hall resistance, von Klitzing discovered in the early 1980s that the resistance in Hall effect takes steps, and the steps turn out to correspond, these are the measured values, they correspond beautifully to h over e square, which in turn, mu sub 0 is now the permeability, magnetic permeability of the vacuum, correspond to the fine structure constant. So it gave us a new way of measuring the fine structure constant. What's beautiful about the quantized Hall resistance is it's not to my knowledge, it's still not derivable from a theory. It's derivable from a model concocted to explain it. But the issue of how to derive it from theory is sufficiently open that for several years, each CoDada report had a section at the end. Are the Josephson effect and the von Klitzing effect exact? Because they had no way to turn to theory to address the question. But here, of course, we have another macrophysically accessible way of getting at microphysically accessible constants. Finally, in the 1980s, initially at Stanford, then in Paris, and we'll come back, it's active now, they took the idea of Compton, and instead of looking at the recoiling electron, they looked at recoiling in the original work, cesium, where they could measure the de Broglie wavelength, give it a monochromatic, by now, laser impulse, and get a change in the wavelength, here expressed as a change in the frequency. That would give them h over the mass of the atom. Plugged into the Rydberg formula, you get a new way of measuring the fine structure constant. CoDada started giving results for the preferred values of the constants. 1973 was their first. They resolved the apparent conflict between Josephson effect and QED. It turns out Cohen and Dumond had made a guess between which of two measurements to include and which to drop. They made the wrong guess. Okay, so that ended that controversy at that time. The amount, starting in 1998, technology had reached the point, and the effort going into metrology had reached the point that CoDada decided they had to do new values every 4 years, which the new values are out now, but the essay describing them is not published yet. The thing I point to is in 1998, they had 29 unknowns and 45 equations for least squares. By 2014, it had jumped to 42 constants in 71 equations. That's possible because computers could do it. It would not be possible no computer could have done it before the 1980s. And I'm not going to read this whole thing. The 2006 celebrates the fact that the values from the, I skipped a slide. Yes, that's the slide. Let me do this. As of 2014, we have 10 different ways of measuring the fine structure constant, to high precision. They involve 5 separate measures, okay? All the attention is gone on the top 2 or the top 3 and 4, because those are the high precision ones. When you get things down to parts in 10 billion, you're getting very, very high in precision. I want to call your attention to something else that I think is just as important. We have 10 measurements here that all agree to 7 significant figures. Okay? They don't agree to 9 significant figures, but they agree to 7 significant figures from 5 different measures, 10 different actual measurements. I could throw, or Graham could throw, 10 more of those up there, more or less in the same ballpark. They're just not worth including in the 2014 report. So we had accomplished, metrologists had accomplished a phenomenal level of converging measurements besides the most precise ones. I'll say it differently. The tendency is to focus on the most precise ones. It's missing how much support the most precise ones are getting from all of the others, and how much they all are giving mutual support to one another and to a whole bunch of others that I can't fit on one slide. Now let me go to what I wanted to do. I'm sorry for screwing up. So in 2006, they described the wonderful agreement between the cesium recoil and the rubidium recoil from Paris, and the QED results from specifically from the hyperfine structure of muonium and hydrogen and deuterium, and conclude this is a truly impressive confirmation of QED theory, which is a great story. But in April 2018, we get a new measurement coming out of Berkeley using cesium, and as you can see in the bottom slide, it is incompatible with the anomalous magnetic moment of the electron value. So we have at the present moment an open question. Is there something wrong with QED, which of course the Berkeley people wanted to say, or is there simply another systematic error somewhere? And that, of course, is going to take time to resolve. At any rate, I want to come back now to our 8 constants. I'm nearly done with the history. By 2014, our 8 constants plus the mean translational kinetic energy were all now being expressed to 10 significant figures. In 1921, this would have been totally rejected as ever possible. You know, essentially 195 years later, we have this in place. It was sufficiently impressive. I do requote Planck. If the theory is at all correct, all these relations should not be approximately, but absolutely valued. These values were impressive enough, and Graham can say much more about this, then it was decided to use them for the new SI. So in 2017, we have the special adjustment. The special adjustment used Faraday's constant, used the gas constant, used the Rydberg constant in fine structures, kind of anchoring everything, came up with these 4 values for the primary terms, Planck's constant, elementary charge, Boltzmann, and Avogadro's number. They then truncated and rounded to make these exact, in the process making the molar gas constant and the Faraday constant. Constant. Okay, the striking thing that I don't know that people realize that these were the same 4 numbers that Planck had singled out in 1900. This is the real culmination of Planck's program, which I'll show you how much so in another slide in a moment. Fair enough, that's the history. It's not proper history. It's okay history up to 1921. From there on, I'm just giving you significant milestones. Every one of them has a huge amount behind them that I'm skipping over, which violates all my principles. So is it evidence of a different kind? Yeah, I want to say definitely yes. Evidence to the effect that a certain collection of interrelated parameters forming a network with one another, they are all constants, they all have values specified at least to so high a degree of approximation, while relying so little on any non-independently corroborated assumptions concerning microphysics. These values are very weakly dependent on theory because of all the convergence. But then the question, using a Howard Stein phrase, yes, but evidence for anything beyond this? Well, we've seen it. It's being taken as confirmation of QED theory, at least that part of QED theory that does the hyperfine structure and the anomalous magnetic moment. It's exposed systematic errors more than once. And in terms Planck used before he began work on black body, which is a year before, units that, quote, will retain their natural meaning for as long as the laws, my insert in question, hold, and even if measured by different intelligences and using different methods, must always remain the same. So the highly precise results I just described are at least evidence for those three things. And I use the phrase evidence for. The question is anything more? Well, I want to claim something more, rather strongly. They are evidence for the permanence of all the many convergent measures of the microphysical constants, each one in its own right, both individually and in concert with one another. What I'm saying about that is those measures are now more robust than any future theory change. And they will therefore act as a constraint on all future theory change. And I say that again with a qualifier to a certain level of precision over a certain envelope of applicability stated in terms that are at least proxies. And the concern here you should all appreciate. All measurement is non-exact, so therefore all evidence for physics is non-exact. We never have any way to verify that our data are coming from a domain that's representative of the universe. We only constantly discover it's not. But we assume it is. And there's absolutely no reason that future theory won't redefine what our terminology is, or at least give a new interpretation. I'm using the word permanent here very self-consciously off of a remark Steve Weinberg made in a paper in 1998 attacking Tom Kuhn. Attacking is a legitimate word. But in it, he says, it's important to keep straight what does and does not change in scientific revolutions. There's a hard part that, quote, usually consists of equations themselves together with some understandings about what the symbols mean operationally and about the sorts of phenomena to which they apply. There's a soft part. It is the vision of reality we use to explain to ourselves why the equations work. The soft part does change. The changes in the soft part of scientific theories also produce changes in our understanding of the conditions under which the hard part is a good approximation. But after our theories reach their mature forms, their hard parts represent permanent accomplishments. And when he was challenged in this point in a letter, his reply was to simply point out he could have done Newton's law. He chose Maxwell's, that they're going to hold in at least a asymptotic limit of any new theory. And in that sense, they are permanent. Okay? So what is it evidence for? Well, what Weinberg referred to as all these mathematical relations, Duhem calls experimental laws. And he, of course, defines quite beautifully a physical theory as a system of mathematical propositions deduced from a small number of principles which aim to represent as simply, as completely, and as exactly as possible a set of experimental laws. And he goes on to say, when you accomplish all three together, you have reason to think you've identified a group of phenomena that form a class unto themselves. My comment is the ubiquity of H, E, and alpha is very strong evidence that they are indeed getting a class unto themselves, with now alpha being the fundamental scaling constant of all charge and field, electromagnetic field interactions. Okay? Somebody like Bas van Frossen, my good friend Bas van Frossen, would say, yes, exactly, that's what the constants show, that's the end of the story. And they are very, very strong evidence for the mathematical part of the theory and its empirical adequacy. I'm not happy with that, so I'm going to ask a further question. The question I'm going to picked up off of my studying of Maxwell's program: to what extent and in what respects have the experiments determining values of the microphysical constants gained experimental access to specifics of the microphysical realm? I'm not going to quote the whole Maxwell quote where he's describing his program to chemists, but he does make this remark: well, we will no longer be accused of mere guesswork. It's a sensible program. If we can get at specific differences in the microphysical realm that reflect themselves in the macrophysical realm, we will be reaching permanent conclusions about the microphysical realm if the evidence for those details is strong enough. That was the Maxwell program for the dynamical evidence for the molecular constitution of matter. The question is, to what extent have the measurements of the various fundamental constants actually realized that? Now, the problem, of course, is they are universal constants. They don't show specifics from one case to another. The only specifics they yield are the masses, and the amount of information you get from absolute masses over 19th century relative masses is very low. Okay, so the question I have, and I'll now do my last slide, the experiments that have been used in the last 40 years to measure fundamental constants, to an outsider, they are mind-boggling complex experiments. Many of them have taken 5 to 10 years to develop before we get numbers out of them that are reliable. More? Longer. Fair. And when you look at the number of assumptions going into them, a lot of them are heuristic assumptions, way of conceptualizing what they're doing, but some of the assumptions are indispensable to getting the numbers you get. Now, the natural question for outsiders to ask is, can you possibly justify the degrees of precision you're quoting? I want to turn that question on its head. We have so many convergent measures. Let's not worry about whether the parts in 10 billion precision is there. Let's accept the fact that we have parts in 10 million for many different measures. That's telling us the experiments themselves are yielding correct values. And that's telling us there's something correct about the design of the experiments themselves. So I'm proposing a program, and it's a program that's going to require a lot of people with a lot of effort to go back through the experiments, look at their logical design in meticulous detail, identify which presuppositions are indispensable to the numbers that come out, and then pose this question: to what extent are those presuppositions evidence that we're gaining specifics? And I'll just end with a kind of example. The anomalous magnetic moment of the electron is telling us that the electron interacts with a vacuum field in more ways than they had realized before that measurement. The Lamb effect, Lamb shift, is telling us the interaction between nuclei and electron is much more complicated. Those are the sort of specifics that I point to, asking, how much does this tell us what an electron is? And my comment at the end, I think a program of looking like this and asking to what degree have we gained access, which is a matter of degree, experimental access to the microphysical realm, is a far more productive research effort for historians and philosophers than to continue to argue about how invalid or valid inference to the best explanation is. Thank you. Well, that's why there's a handout.
I need to take this now. I mean, I just pick up on one thought, which is that when there's convergence of results, you don't want to sort of
pay too much attention to the thought that it could just be a fluke or coincidence. Physicists want to, at least in certain contexts, want to resist that thought. On the other hand, scientists are willing sometimes to accept that there have been flukes and coincidences. And
Of course.
you gave one example, which was the result of the fine structure formula being derived both from Sommerfeld's theory and from Dirac's theory, which you said have no more in common than special relativity. Now, physicists looking back on that have seen it as a puzzle. Some physicists have wanted to resolve the puzzle by giving some sort of explanation because they feel it can't just be a coincidence. Other physicists have described it just as a fluke or just as a coincidence. I think it behooves scientists to explain it as not just a fluke, but something to do with the relationship of the mathematics between Sommerfeld's theory and Dirac's theory. And you can show that they do have more in common than just special relativity, or it doesn't seem like it on the surface. But what you can first start with is showing that there's a commonality between Bohr's theory and non-relativistic 1925 quantum mechanics. There's a relationship there because you can show that in the semi-classical limit of the Schrödinger equation, you get it sort of reduces to the Hamilton-Jacobi formulation of classical mechanics. Because you can start with that relationship there, once you've shown there's a relationship in the mathematical level between Bohr's theory and the 1925 quantum mechanics, it's no surprise that when you then make those two theories relativistic, as Sommerfeld did to Bohr's theory, as Dirac did to the 1925 quantum mechanics, then you also get a relationship there. So there's a story you can tell about how that wasn't just a fluke.
I did not call it a fluke.
No,
What I did point out,
I've seen scientists call it that.
okay, I did point out the equation is a lot more robust than any theory it's derived from. Isabel quoted J.J. Thomson in 1903. Theory is an instrument for doing research. That's been my life story. And as a philosopher of science, theory is way overemphasized in the philosophy of science. It ought to be viewed as an instrument for getting at what's going on in the world. And this is an example. On the other hand, there's a beautiful letter from Sommerfeld to Dirac. And the phrase I remember from it is, at least I was right that you needed relativity theory. Okay? I mean, the spin of an electron is nothing in the Sommerfeld theory. But of course, that's where the fine structure constant is coming from. Second, you bring up the Hamiltonian, and you know this from a paper of Theroux's and mine. There is a certain difficulty with the fact that the same mathematics applies in two situations to whether you're really talking about the same thing. Okay? A huge amount of microphysical theory is being related to classical theory through Hamiltonians and Lagrangians. And the question always has to be asked, is this by analogy or is there more to it? And I don't know that those answers are quickly forthcoming at the present moment. That may be a comment about me. But I'm very reluctant to sit here and make strong statements about those relations. Theroux, in the paper Theroux and I wrote, we make the comment, yeah, you can measure the rotation of a diatomic molecule, and with it, the distance between the two nuclei to 4 significant figures, providing you take the equation in question to be an equation for rotation, because it is classically so. Wouldn't you like to have a little more evidence? And Theroux points some of that out in our paper, a little more evidence that it's not mere analogy. But that's always the difficulty if the strongest evidence is for a formalism. And that's, of course, the point Weinberg was making. The formalism is robust. The interpretation of it is far less supported by any evidence. Okay? And that's one of the points I wanted to make. But that's also why I want to concentrate on the achievement of these numbers and what it tells us, what the experiments tell us about them has to be true of the microphysical realm for the experiments to have succeeded. Finally, convergence is the classical, well, stability is the first way to figure out you're not just got an artifact, okay? It's a standard test to make sure you don't have an artifact. Cavendish in his original experiment varied nothing but the torsion rod, because the initial results might have been a feature of the torsion rod he used, and it turned out not to be. The most powerful way to conclude you're not dealing with an artifact of an experimental setup is to have the same values by convergence from a totally complementary measure that isn't assuming the same things at all. And one of the examples is the quantum Hall effect. It is not assuming QED treatment of Lamb shift or of the anomalous magnetic moment. And that was the realization in 1969 that Taylor, Parker, and Langenberg had. The precise measurement of the constants could be a form of evidence to make sure this abstract formalism of QED was something more than an abstract formalism. At any rate, I don't disagree with you. I'm just, I don't use the word fluke when I see 10 significant figures from 2 complementary measures, okay? I mean, if nothing else, I hope everybody comes away with just one thing I said. In 1921, these numbers of significant figures would have been considered beyond human capability. And they were good physicists in 1921.
Yeah, so I guess when I think about physics, I think theory is the main thing that matters. So I guess I'm on the opposite side of you. So then when you say it's just an instrument for figuring out what's going on in nature, I really have no idea what you think is going on in nature without having theory tell me what's going on.
Well, of course, I'm making the point Weinberg. Theory is mercurial. It's something we invent over and above the data. The main use of theory, time and again, is to provide means of measurement and interpretations of those measurements locally. The rest of the theory isn't needed to derive all the measures I have here. Very small, limited parts of it are. I understand theory is celebrated, you get Nobel Prizes, etc. But as Weinberg would tell you, we don't have a real theory yet. We have a group of effective theories. Until we have a real theory, we're out in the woods. That's Weinberg speaking, not me. He's the one who invented the term effective theory, and he says all our theories at the moment are only localized effective theories that we do not have the means to assess because we don't have a broader theory yet. I'm not against theory. I'm simply saying we way overestimate its importance to science.
I can agree with that. The question, what do you think then? Reality, you said that theory is an instrument for us.
I mean, I'll give you an example. Fair enough. J.J. Thomson, there's an example I've used in classrooms for 40 years. J.J. Thomson, in his measurements of charge to mass ratio, used theory to take what we now call the electron to be a particle. Of course, that was totally not needed for his measurements. He just couldn't conceive otherwise. So it's very nice his son got the Nobel Prize for showing electrons are waves. Okay? It's just the heuristic we impose in thinking about experimental results. That is a heuristic, Einstein's word in the 1905 photoelectric effect, in the title to it. It's a heuristic that may very well be discarded because it's overreaching the evidence all the time.
Like experiments are also heuristics.
No, experiments can deliver really solid results. I've just shown them to you. Okay, complementary experiments. And they last a long time. Huygens' measurement of surface gravity originally just outside the Hague is our current value to up to 2 digits in the 4th significant figure. And as I said, we continued to use the same measure until we got spaceships. This is true in place after place in physics, as a matter of fact. Isabel's talk on the measurements of the density of the Earth, mean density of the Earth, give you the same story. What I want to emphasize, I study evidence in physics. That's all I study. Evidence is a historical process. You cannot look at evidence in isolation. You have to look at it in terms of the questions that were on the floor at the time. The impressive thing about the history of physics is the extent to which evidence has been cumulative. Okay? I have a joint paper with Jed Buchwald, who the two of us wrote the elogium for Tom Kuhn, responding to Tom Kuhn, and it's called The Continuity of Evidence. And the point it's making is that conceptual frameworks change all over the place in discontinuous ways. There has been a remarkable continuity of evidence. In the case I study all the time, orbital theory from Ptolemy to the present. And similarly in gravitation theory from Newton forward, et cetera. When you look at it that way, some of the explanations we give, to use Weinberg's term, for why our equations work are clearly inventions by us to allow us to conceptualize what we're doing. But as far as supported by the evidence, that can be very dubious. I'm preaching, I'm sorry, but that's at the heart of 40 years of work that I'm saying this.
I want to ask a follow-up to this, though, because I mean, I'm, as you know, very sympathetic to this project and everything about it, but I think one of the worries that maybe Casey has, I don't want to speak for him, maybe someone like Boss has as well, that allows him to keep saying the things that he wants to say, is that insofar as you need the theory in the soft sense to talk about what the evidence is or what the evidence is for, it looks like it's going to be very difficult to abstract away from that, leave that behind, and just talk about. So I mean, you have to do this somehow if you're talking about the continuity of evidence across theory change. You have to have some way of saying, but what is that thing? What is it saying about the world in a way that's independent of the theories that have changed, as it were? And I think that's possible, but I think that's a challenge that's posed from the side of the anti-realist, or the person who wants to put this heavy weight on it, because it looks like it's the theory that gives you the language for describing the evidence. And if you want to say it's just the number, then that's very difficult, because the number by itself isn't saying anything at all. You have to attach that number to some sort of...
The numbers are parts of an equation. The numbers don't stand on their own. Look, I, of course, am in contact with Boss. My accusation is Michael Friedman's accusation as well. Boss is overly centered on theory. So he's very interested in my work on theory-mediated measurement, but unlike me, he wants to emphasize without the theory, you don't have the measures. I've just shown you a huge amount of evidence that you have the measures independently of theory. They are more robust than theory. Now the question, what parts of what Weinberg calls the soft parts are actually supported by evidence? That's what I'm talking about when I say, start talking about gaining experimental access. I think it is possible to get those soft parts hard, but it's got to be through experiment that's highly discriminating. Okay, but let me answer your question in a different way. I have the paper I guess I'm now best known for, Closing the Loop. I make a proposal at the end, and it's at the heart of everything I think about physics and chemistry. What we know now that Galileo did not know is somewhere in the millions of details of things in the world that make a difference, and to very high approximation, what differences they make. Okay? In the case just of our planetary system, we have somewhere, I've done a count, in the order of 10,000 details that are making a difference to planetary motion. Hill-Brown theory has 1,500 perturbation terms, to give you a feel. Okay, that's what we have come to know. Theory is indispensable to it, but particularly mathematical theory. We can run counterfactuals all over the place. That's a great form of knowledge. Much of it, hopefully, is microphysical. Okay, but I'm content with that. I don't feel the need for a universe, for Steve's final theory, except to have more confidence that all the data they presently have isn't parochial as hell. I mean, what did we learn with general relativity? All the data we had to support gravity theory was from a totally parochial situation, totally non-representative. Okay? There's no way to discover that looking at the data. continuing theory is indispensable for that, okay? So I'm not dismissing theory. It's the last thing I want to do. What I do want to emphasize is look carefully about what the evidence actually establishes for any theoretical claim. And very often, you will see that's only a heuristic. It can be replaced. When Milliken dismissed Einstein's quantum theory of light, his next paragraph was, it can obviously be derived from many different theories. He didn't offer one. He just said it could be. That's the constant worry you have with theory being the center. Same very supported results can be derived from very different theories. We've seen it time and again. The impressive thing is the extent to which that has been cumulative rather than destructive.
The queue has become long.
Yeah, I'm sorry.
Well, I don't need to say that. You said everything. I was going to say, look, thank you. It was a great talk. Really, really enjoyed it. And I'll take away your paper to digest it. Just to say, just as a taste of my talk later in the afternoon, is an example of convergence happening in reality, because to actually get a value of the Boltzmann constant, we used a number of completely independent physical approaches, which have completely different underlying physical theory, and yet you get the same number. And those equations, the perturbation effects have had to be pulled apart to the nth degree. And again, those perturbations are different for each approach to understand how to get to the lowest uncertainties on those approaches, and yet they still converge to the very low uncertainties. So it's a really powerful test.
I just want you all to know that young Huygens, Newton was an undergraduate when he did this work. In fact, Newton hadn't entered Cambridge when he did the initial work. Huygens knew how to do measurement. He intentionally found convergent complementary measurements. And 4 of them, starting with 2, because he recognized the need to do it and succeeded, okay? So the history of theory-mediated measurement is a history of finding complementary measurements that converge. Ptolemy tells you to do that, but of course he doesn't have experiment to be able to do it.
Thank you very much for this talk, which will give me a lot to do.
Well, it's complementary to your talk, and you bailed me out for something.
Magnificent. And I was just, it's not something against convergence, what I'm going to say, but shouldn't we be cautious, or at least it poses problems, because in search for the systematic errors, when you know what the others have already had, even if you are doing an experiment which is based on different measurement principles, different theories, etc., the fact that you know what you should arrive at makes you look for systematic errors and then converge. Well, this is what's called the bandwagon effect or whatever. And I have understood, maybe you could say something on that, that now in order to prevent this effect of converging towards this value that should be obtained, you fudge someone comes in and...
They did that for the Planck constant.
Yeah.
The Boltzmann didn't need to do that.
Yes, well, and other metrologists said to me, oh yes, I know that this is possible, but we don't do it. In order not to know exactly what which number you are actually getting in your experiment, because someone has put in a shift, and therefore not trying to get the right values. So, and I believe that some of the NIST measurements are suspected to have converged to the right value because of wrong reasons. But I'm not a specialist in that.
I don't know about that.
Well, I was told by meteorologists that this is a fishy subject. So what you, well, it's just that we have to be cautious about this convergence, or at least how it is brought about, because in fact we could all converge to a biased thing and discover, like with the Josephson effect, that everyone was biased, and then the story goes.
May I say one thing before? Yeah. I think provided the experimenters actually publish how they have derived all their corrections and how they have pulled apart the equations to actually understand where those corrections come from, I think the test of objectivity still remains. So only when they don't do that, they just, and I have to say there was at least one Boltzmann paper where they don't do that, which I say which I'm suspicious of, because they get very lengths with very low uncertainty. But providing the experimenter has done that, so it's open for everyone to examine and interrogate, I think the objectivity remains.
I was told that the problem with the task group is that they received calculated uncertainties and lots of information about how the experiment was made, but in fact they have no time to go really into it and see if actually the numbers that are published or given are really, so
The task group alone hasn't got enough
yes.
expertise to do it for everything. The community has to.
That, and that's what I was going, it's a complex response. First of all, we're pursuing precision because it's the most powerful way we have of testing theory at the forefront, okay? And it's very important. No less important is all the other measures that help substantiate one another. And that convergence is very independent of one another, first. Second, I have a very, very deep trust, first of all, in the community, because the one thing about physicists is they're always trying to find something wrong with one another. And that's a virtue, a great virtue. I gave the Milliken example because for 25 years that was actually a seriously wrong example that nobody could believe Milliken could have made a mistake that simple. He didn't make it, his graduate student made it, okay, measuring the viscosity. But the thing you must consider, and you paraphrased me last night on this very point, one virtue of physics is as a response to you, we're constantly taking past theory and presupposing it in continuing work, and it's being tested all the time, usually en passant, without anybody being aware it's being tested. And in the long run, that's going to expose. My faith is in the long run self-critical capacity of physics as a continuing community to expose things. And I included the Bearden. I trust nobody in here had probably heard of Bearden. But he made a huge difference historically because he stuck with his result when it was discrepant. Okay, he did not back down. He actually continued the work at Johns Hopkins for another few years, making it better, stronger, and stronger. The title of my paper that I'm referring to is called Revisiting Accepted Science, the Indispensability of the History of Science to the Philosophy of Science. But it's the revisiting process and the extent to which that is done effectively that gives the sciences that do it their epistemic standing. Sciences that don't do it, and I can start naming them very quickly, you can tell the difference. There's no cumulative development of evidence at all, okay? But, I worry less about artifacts in the short run because I'm not a practicing physicist, but looking at it at the outside, if there's an artifact like the Milliken E, it's going to be exposed so long as we have another way at the same value. We don't have any other way after G, okay? And every CoDada report complains about that all we have is some variant on the Cavendish experiment, okay? And it stands out. G is, what, 5 significant figures less precise than any of the constants that we were talking about here. It's 10 to the minus 5th is the, yeah. So there are 2 things going on here. Where you get into an area of interlinked constants, and I repeat, that's the most important thing I wanted to get across. When you have constants interlinked, you have capacities to do things that you do not have when they're not interlinked. G is not interlinked with anything else. We are trapped. Okay? And the only thing that strikes me about this whole thing is the extent to which Planck foresaw the possibility, not of precision, but at least of this as a way of evidence.
Can I just add, I think that, maybe just to summarise in a sense, that the experiments will win out.
Yeah, absolutely.
In the end. Because the experiments show up where the theory is deficient. A theory is only as good as the last experiments prove that it isn't whole.
The April 18th paper, April 2018 paper, I stumbled across only about, 10 weeks ago when I sent it to the 2 of you. And I assume the community still hasn't figured out how to respond. There's been one paper from Paris that Alistair found that in effect said we can't do, go ahead.
Well, what's interesting was that the Paris group, they were trying to improve the precision of their measurement, and they would have liked it to match the Berkeley group.
That's rubidium they're using.
But what was interesting is even with the same method, they were dealing with different systematic errors. But I think they would probably use this technique you described to ensure that they weren't building in matching the Berkeley group if they could get the precision tight enough. But then the whole point of those 2 papers, I think, is the Berkeley group says this is exposing new physics, because they say, now we have evidence against this dark photon explanation for this effect and this discrepancy between these 2 measures. And of course, the Paris group says, well, hold on there. We don't really have that evidence until we can get the same result using the same method. And so in that case, it is really, really important that they do exactly this process you're talking about, I think, to ensure that they don't converge, because there's this thing at stake, the discrepancy in these 2 different ways of getting at the fine structure constant.
Which group is it?
LKB.
Yeah.
Francois.
Yeah, they did the rubidium work. The original work was done at Stanford on CCM, and the Berkeley group is redoing the CCM measurements.
Sure. Thank you so much. I really, really enjoyed all yours and Isabel talks that are wonderful. I guess I have a sociological question here. I want to put really playing the devil's advocate actually, I don't believe in this. I was struck by the story in Isabel talk about, I can't remember the name of the scientist, he said, I'm working for the universe. Boys, that's right. And Planck here that says, in a kind of visionary way, those values are absolutely valid.
Remember, he says, if this theory is at all correct, then.
Yeah, so exactly. So that brings me to my question. That obviously, for Planck, and I'll go back to this actually in my talk, as I read it, Planck was launching obviously his research program. So for him, finding all this beautiful agreement was evidence for the validity of his quantum hypothesis, was a way of gathering consensus around this theory. And so I wonder whether there is some sociological story in how someone at some point has this visionary stance and launched a program that in a way sets us all on a trajectory that we still are. And obviously nature is nature and mathematics is mathematics, and those values are there and they are be found again and again and measured with more and more precision in different ways. But I wonder whether whether you have any thought about what Rutherford once said about Galileo. We all stand on Galileo's creed today.
Well,
And also Planck's creed in a way, in this interrelational constant. You can set us on a path that we still are.
You're asking a very complicated question historically, and as anybody who's done history, and I'm not a historian, realize it's always so much more complicated than you wish it were. Planck comes out of several years of interacting with the group of physical chemists, Ostwald primarily, whom he was in direct communication with until he finally gave up on Ostwald. Nernst was Ostwald's assistant at the time, and Van Hoff and Arrhenius were working. They created a field in the 1890s. Planck was anti-atom, just as they were, or at least, I should correct myself, at least as Ostwald was. But there's a whole context in which Planck is saying that in 1899, okay? And taking that statement out of that context and making it appear to be a biographical remark about Planck is misleading. What really is happening is Planck is trying to think about the controversies at the time over atomism, which were very intense. He knew the Meyer book. He actually references the Meyer book in that paper, the German edition, of course. So he knew that in a certain sense, there was a beautiful program that Maxwell had conceived. And I'll come back to that in just a moment, just with a quick remark, that Maxwell had conceived and it had failed. It had been, not failed, it had been very disappointing. And Meyer says the problem here is we're assuming they're spheres and we have no evidence that they're spheres. Okay? So it didn't take Jeans in 1921 to say that. Meyer is already saying it in 1899. The Maxwell program, I'll now say something autobiographical. I came to understand Newton's Principia after teaching it once cover to cover from reading Maxwell's Dynamical Evidence for the Molecular Constitution of Matter, because if you notice that quote I did not quote, he says the safe way to do science is to assume an absolute minimum and let phenomena deduce from phenomena the theory. That's pure Newton. And it was not anybody else but Newton in that tradition beforehand, other than Ampere. Ampere said the same thing. But that was a rare view, and it's almost, it didn't exist in philosophy in the 20th century. The thought was everything is hypothesis and testing. For Newton, for Maxwell, that's bad science almost always. Or I'll rephrase it. That's science that gives you very weak evidence compared to what you could get if you let theory be used as an instrument to deduce things from phenomena. And that's where theory is indispensable, but not the whole framework. Pieces of theory are indispensable. Okay? But, you know, I'll add one last remark back to the community. I said this to Graham yesterday after Nadine's talk, and it's a striking moment to me. Sam Schwaber told Steve Weinberg that his popular book, he should have me read it before in manuscript and correct it. And Weinberg didn't know what he was getting into, namely 200 to 300 hours of phone conversations over a 5-month period. But at one point early on, and I didn't trust the man at all, I regarded him as a supremely arrogant jerk. I made a remark to him that probably the biggest difference between him and me is the amount of weight I put on the whole community, people nobody's ever heard of. And his reply was, you can't put more weight on that than I do. And I think that's a deep point. One of the 2 or 3 leading theoretical physicists of the 20th century says that. That's the safe thing about physics. It has a community like that. And it's had it essentially since the 18th century. But be that as it may. I mean, I think it is a sociological phenomenon, but it's a sociological phenomenon arising out of the complexity of a subgroup of humans forming a longitudinal chain internationally, working on the same set of problems over a long, long period of time, and doing so honestly and having one another criticize them. That tradition, which started in the 17th century, that tradition has been singular to the physical sciences and more recently to the biological sciences. It has not occurred in the social sciences. But I think it is a social phenomenon, but it's a social phenomenon of creating these sub-disciplines populated by these weird people who worry about the significant figures of their careers. I can't express how much admiration I have for doing that.
Can I just a follow remark on that is we experienced this, of course, in our community when we work towards fixed values of the Boltzmann, because people who used the same technique particularly were very robust in challenging other people who used the same technique if they were not getting agreement, to the point where it actually sometimes broke relationships because it was a very robust challenge.
Well, the quote,
It happens and is alive and well today.
the specific quote I gave from Paul Foreman at lunch about Barry Taylor is, who is Barry Taylor to say this group of measurements aren't going to be considered at all? And my answer was, go read the argument in the report for why they are not being considered. Because that's the beautiful thing about CoDada reports. They don't come out for a year or two later, but when they come out, they tell you what they did. As you know perfectly well because you've been doing it. Sally.
It's only 5 seconds.
No, I mean, I think you should ask your question.
Well, it's only 5 seconds because I just wanted to pay tribute to you, George, and you titled here at the end a proposed research programme. Just wanted to point out just how humble that is in terms of your question here, because what you're actually trying to do is change the way that we do philosophy of science, and what you've been doing for so long has been a different way of doing philosophy of science. And it's not just about using history of science, which a lot of people think. There's different ways that we can use history of science, and you have a very particular kind of way of looking through the evidence to take that to philosophy.
It's a nice remark from a former student who knows my work very well, but I trust you realize that's never been my goal. My goal is to understand evidence in physics, and I found most of philosophy of science useless to my purposes 40 years ago when I started looking at it. So I knew I had to do it separately. And I've never tried to change the field. That's up to the field.
Yes, well, I think that's what you're doing.
Well, I question that, but that's... To change the field, you have to engage people in the field. I generally don't engage people in the field.
I think we should thank George.
Thank you.